So for this exercise, we are interested in the rational zero theorem. Now let me throw a few things at you here. Zeros can be both real or imaginary. If they are real, you can see them. If they are imaginary, you cannot see them. The real variety can be rational or they can be irrational. Allow me to explain. Look at this picture here. Say we look at this diagram. So this is a function that has a degree of 3. Because it has a degree of 3, you owe me 3 zeros. I just don't know how many of them are real and how many are imaginary. And of the real, how many are of each kind. So I just sketched a picture that could possibly represent this. Do you need a picture? No, but I'm just trying to show you some things. Now, I can see here that I have 3 x-intercepts. So because this function has 3 x-intercepts, I can see them. I can guarantee you that this one has 3 real zeros. Are they rational? Are they irrational? We'll get to that. But the point is, this one has 3 real because I can see them. This one here, the degree is 4. So you owe me 4 answers. I have 1 answer there. I have another answer there. So I can see 2 of them. So 2 of them are real. But since you owe me 4, that means that 2 more are going to be imaginary. I can't see them, obviously, because they are imaginary. How do I find the 2 missing zeros? We'll get into that in just a moment. One more quick picture. Here, you look at the degree, which is the highest exponent, if it's in standard form. So, you owe me 6 zeros. I need 6 of them. Let's see what we have. 1, 2, 3, 4 of them are real. So I can see that 4 are real, so 2 are imaginary. Another thing, of the 4 that are real, you see how this one, that's a pretty nice number. You see how this one, that's a pretty nice number. And these ones, those are really weird. So when I say nice number, I mean rational. And when I say like weird numbers that are unpredictable, those are irrational. So the device and the instrument that I'm about to give you has the ability to detect zeros that are real, rational. So I am going to show you how to find zeros that are real and rational. And all the leftovers, meaning the irrational real or the imaginary, we will find these in a different way. But first and foremost, we have to know how to find these ones. Find these first, deal with these later. So let's try one problem here. So looking at this function, the degree is 4. So you owe me 4 answers. And as a matter of fact, I am going to start an answer key and I'm just going to sort of box this in. And I'm going to open up a little brace like that. I'm going to close the brace and I am going to open up 4 slots because we owe the teacher 4 answers. Now, just by looking at this, of the 4, how many are real versus imaginary? I have no idea. And I am not going to make a picture. I am not going to graph. I did the graph just to communicate the concept. We're going to do this completely by hand. So here's what you have to do. You see this number in the back, 4? Write down all of the factors of 4, the numbers that go into 4. So 1, 2, and 4 are all the numbers that go into 4. Now, look at this number here, 9. What are all of the numbers that go into 9? 1, 3, and 9. Don't worry about the negative for now. Just look at this number, look at this number. All the factors of this or this. All the factors of this or that. Now what you have to do is you have to take this set and divide it by this number first. So if I take 1, 2, 4 and divide it by 1, I get 1, 2, 4. Now take this whole set, but now divide it by 3. So 1 divided by 3, 1/3. 2 divided by 3, 2/3. 4 divided by 3, 4/3. Now take this whole set and divide it by this number. It's always like that. So now 1/9, and then 2/9, and then 4/9. And what you want to do is put a little bracket, put a plus or minus. Are these the answers that I put in here? No. These are candidates. I like to use the word candidates. These are possibilities. You know how we are trying to find all of the zeros and we are initially trying to find the rationals? All of the rational zeros of this function are hiding somewhere in here. We don't know which ones of these work. We don't know which of these don't work. And it's all of these is positive and all of these is negative. So if they ever ask you to make a list of all the possibilities, this is how you create that list. You write the factors of this, you write the factors of that, and you divide this set by these one at a time. Protect them, plus or minus. Now we must proceed to actually find the zeros. And for that, we need the rational zero theorem. And this is how this works. We're going to need synthetic division. Drop in these coefficients in here. -9, 39, and so on. You see how this was x4, x3, x2, x constant? If there was a gap or a jump in the x's, if there was an x power missing, you would have filled it in with a 0, but there was no need for that because there was no missing power of x. Now, this number always goes down. And as soon as I draw my synthetic division, I like to draw a little bar because that number is going to be the remainder. So this is how this works. Randomly pick a number from this collection to test it. For instance, I want to test the number 1. So I'm going to put a 1 right here. And this is how this works. Multiplication, so this times this, that, and then addition. Multiplication, addition. Multiplication, addition. Multiplication, addition. You see how this is the remainder? The remainder has to be 0. If it's not 0, that means that this number was a fail. So this one was a fail. So let me try this again. And it's really good if you have like a whiteboard where you don't have to erase, you can just scribble it off. So let me try -1. So let's see. This times that is 9. Add them, 48. Multiply, -48. Add them, -27. Multiply 27, add them 4, multiply -4, add them. Ooh, this works because the remainder is 0. So -1 is a winner, ding, ding, ding. And I am going to throw it into my collection. So I have found one answer. I just need to find 3 more. So what you can do, since these numbers were a success, you can actually build from here. So now instead of testing the originals, I'm going to test these numbers here. And now I'm going to go like this, because now this is going to be my remainder. So what numbers should I now test? The winning number sometimes works again, but let me test a different number. Let me test one of the fractions. If ever you have a bunch of fractions, more than likely one of them is going to be a winner. So let me drop this number again. You always drop that first number. Now pick a fraction. It doesn't matter which one. Let's say I pick 2/9, for instance. Multiply, add them, multiply. Look, if I multiply this and this, it's not going to be an integer. It's going to be something weird. So that alone makes me suspicious. So I'm not going to continue with this because this and this is going to be something that's not an integer. That's just a gut feeling. So let me just scratch that off and try a different number instead. What about -2/9? That times that is +2. 48 plus 2 is 50. 50 times that is a weird number. So I'm not going to waste my time with 2/9. Scratch it off the list. Let's try a different fraction. How about 1/3? So 1/3 times that, that's -3. Add them, that's 45. That times that is 15. Add them, that's -12. That times that is -4. That actually works because it's a remainder of 0. So another winning number was 1/3. Now let me say this to you now. Can I continue doing this over and over and over? Yes. Is that gonna guarantee that I find all the answers here? No, because again, remember, sometimes your answers are rational, sometimes they are irrational and imaginary. So here is a suggestion, so listen up here. You owe the teacher 4 answers. You have found 2 of them. As soon as you have 2 answers that are left to be discovered, you can build a quadratic with these. So here's what I'm saying. This is a remainder, this is a constant, this is x, and this is x squared. You build it right to left, where this is remainder, constant, x squared. So this is the equation that I have. Negative 9x squared plus 45x minus 12 equals 0. Now you have to solve this quadratic equation. You can solve it by factoring, quadratic formula, whatever. You know what I see? I can actually divide everything by negative 3. I can reduce everything by negative 3 to make the numbers easier to look at and easier to deal with. So now that I have this, let me go quadratic formula, where this is A, B, and C. So quadratic formula is negative B plus or minus the square root of B squared minus 4AC all over 2A. So do these problems take a while? Yes, sir. But you know what? They're very predictable and they always follow sort of the same pattern. Let's see here. So this is 15 plus or minus that minus that. I think that's like 187, I believe, over 6. So what I can do now, 177 rather, what I can do is, because the square root of 177 is weird, I'm just going to write my answers. So I have 15 plus square root 177 over 6. And then the other answer is the negative version, 15 minus. Yeah, the other answer is the subtraction version. So there you have it. I have 1, 2, 3, 4 answers. As it turns out, all 4 of these are real. They are imaginary when they have i's. Like if I had square rooted a number that was negative, that would have been I imaginary. So this one had 4 zeros. 2 of them were real, rational, and the other 2 were real, irrational. This is called the rational zero theorem, and it only has the ability to detect zeros that are real, rational. I decided to go to quadratic as soon as I saw 2 numbers left. Did I have to? No. You could have continued this synthetic division process with some of the other numbers. It is your decision how to approach your problem. Now, did I cover all of the different cases and technicalities concerning the rational zero theorem? No. Did I say everything that I wanted to say? No, because that would have taken like an hour minimum. So try what you've learned in this video with your problem, and let's see how it goes.